Have you ever wondered if time travel is possible, or if it's just a concept limited to science fiction novels and movies? The prospect of hopping into a time machine and exploring different eras, rectifying past mistakes, or peering into the future has long intrigued us. In fact, time travel is a staple in the realm of science fiction, from H.G. Wells' The Time Machine to the Back to the Future series. But is time travel confined to the pages of novels and the frames of celluloid, or is there more to it? Theoretical physicists have long debated the possibility of time travel. The subject is complex and riddled with questions. Can we travel back in time? Can we alter the past? The consensus on these questions is still pending. However, there's one aspect of time travel that physicists are pretty sure about: traveling to the future. Yes, you heard it right. Traveling to the future, contrary to what many might believe, is not merely a figment of a science fiction writer's imagination. It is a concept that finds its roots in the groundbreaking work of one of the greatest minds in the history of science, Albert Einstein. Einstein's theory of special relativity, proposed in the early 20th century, revolutionized our understanding of space and time. The theory introduced the concept of time dilation, suggesting that time is not a constant entity as previously believed. Instead, it slows down as you move faster through space. So, if time travel is possible, how does it work? Let's delve into Einstein's theory of special relativity to find out. We'll explore how time dilation facilitates travel to the future, how GPS satellites utilize this concept, and how interstellar travel might someday allow us to journey years into the future. We'll also discuss why, despite these fascinating possibilities, we haven't yet mastered the art of time travel. So buckle up, because we're about to embark on a journey through time. Albert Einstein, in his special theory of relativity, introduced a phenomenon called time dilation. Now, this might sound a bit spooky, but it's actually a pretty straightforward concept. It simply means that time slows down as you move faster through space. Picture it like this. You're on a high-speed train and the landscape outside seems to be moving slower than it actually is. That's kind of what happens with time when you're zipping through space at high speeds. Now, a central part of this theory is something Einstein called space-time. This is where he fused the three dimensions of space length, width and height, with the dimension of time, into a single term. He envisioned space not as something flat and rigid, but as something curved and flexible. Imagine this: you've got a trampoline and you place a heavy bowling ball in the center. It creates a dip, right? Now, if you try to place a smaller ball on the trampoline, it will roll towards the bowling ball. This is because the bowling ball has created a gravitational dip in the trampoline. In Einstein's vision of space-time, the same thing happens on a cosmic scale. Heavier objects, like planets and stars, create dips in space-time, and these dips affect how other objects move. The closer an object is to the center of the dip, the faster it moves through space. And here's where time dilation comes in. Because time slows down as you move faster through space, it means that the closer an object is to a heavy mass, like a planet or a star, the slower time moves for that object. In other words, if you were to stand on the top of Mount Everest, time would actually be moving slightly faster for you than for someone standing at sea level. This effect is incredibly tiny on Earth, but it becomes significant when dealing with astronomical distances and speeds. So, in essence, the closer an object is to a gravitational source, the slower time moves for that object. But how do we see this effect in our everyday life? Let's delve into that in our next scene. To see time dilation in action, you don't need to go far. It's happening right above us, in the GPS satellites orbiting the Earth. Now, these GPS satellites are not just roaming around aimlessly. They are located approximately 20,200 kilometers above the Earth's surface. Each of these satellites carries a highly precise clock on board that keeps ticking away accurately to the microsecond. But here's the interesting bit. Due to the phenomenon of time dilation, these clocks gain an average of 38 microseconds per day. You might think, goodness, well, what's a few microseconds between friends? But when we're talking about global positioning, these microseconds make all the difference. The GPS satellites rely on their onboard clocks to maintain precise positioning. If the clocks were to run even 38 microseconds fast, it would result in a positioning error of nearly 10 kilometers. That's right, 10 kilometers. Imagine you're trying to navigate your way to a coffee shop or a friend's house, and your GPS is off by 10 kilometers. You'd end up in the middle of nowhere. That's why the time difference is constantly corrected to ensure accuracy. accuracy, but why does this time dilation occur at all in the GPS satellites? The answer lies in Einstein's theory of special relativity. According to this theory, time slows down as you move faster through space. These satellites are moving at high speeds, and the farther they are from the center of the Earth, where gravitational acceleration is strongest, the slower time moves for them. This is why the onboard clocks of the GPS satellites experience time dilation and gain microseconds each day. So we've seen how time dilation affects our daily lives. But what about on a larger scale? How does it affect time travel? The movie Interstellar provided a dramatic and visually stunning demonstration of time dilation. This sci-fi blockbuster, starring Matthew McConaughey, presented a situation where time slows dramatically because of the intense gravitational influence of a nearby black hole. In the movie, McConaughey and his crew land on a planet with a gravitational pull so strong that time itself is affected. For every hour they spend on the planet, 7 years pass on Earth. That's a pretty significant time difference, wouldn't you say? The result of this is a stark age contrast between McConaughey's character and his daughter back on Earth. When he returns, he's barely aged a day, while his daughter has become an old woman. This scenario, while cinematic, is a representation of a real physical concept. It's based on Einstein's theory of relativity, specifically the phenomenon known as time dilation. Time dilation is the idea that time passes at different rates in different gravitational fields and at different speeds. The stronger the gravitational field or the faster the speed, the more time slows down. So, in the vicinity of a black hole, where the gravitational field is immensely strong, time would slow down significantly, just like in Interstellar. But if this is the case, you might be wondering why we haven't made such drastic leaps forward in time ourselves. The answer lies in our current technological limitations. We'd either have to take advantage of the intense gravitational acceleration caused by black holes, like in the movie, or send a traveler rocketing into space at close to the speed of light. With our current capabilities, we can only manage to jump a few microseconds into the future, like with GPS satellites. But who knows? As our understanding of the universe and our technological prowess grow, we might one day be able to send a human into the future by traveling close to the speed of light. While this is a dramatic example, it raises the question, why haven't we made such drastic leaps forward in time? The ability to jump forward in time hinges on one key factor: velocity. You see, in our current technological landscape, we are limited in how fast we can propel ourselves through space. This speed, or lack thereof, restricts us to mere microseconds of time travel as observed in our GPS satellites. But what if we could go faster? Much faster. Let's explore this idea. Imagine we could harness the intense gravitational acceleration caused by black holes, or even achieve speeds close to the speed of light. What then? According to Einstein's theory of special relativity, time slows down as you move faster through space. Therefore, if we could reach these astronomical speeds, we could theoretically leap years, even decades, into the future. But here's the catch: achieving these speeds is currently beyond our reach. We're talking about velocities in the vicinity of 1 billion kilometers per hour. That's more than 66,000 times the speed of the fastest manned aircraft ever built, the NASA X-15. To put this in perspective, at that speed you could travel from New York to London in less than a blink of an eye. But let's not get disheartened. Just as the horse-drawn carriages of the 19th century gave way to the supersonic jets of today, our current technology too will evolve. Perhaps future advancements will allow us to overcome these velocity barriers, allowing humanity to make significant leaps forward in time. So what does the future hold for time travel? Well, that's the exciting part. We don't know. The possibilities are as infinite as the universe itself. Will we one day be able to send a human into the future? Will they be able to return and share their findings? These questions, while currently unanswered, drive our curiosity and innovation. While we may not be ready to jump years into the future just yet, the concept of time dilation and its implications for time travel continue to captivate us. As technology advances, who knows what the future holds?